This is the second question I would like to solve. It involves a deep member design. Relatively low strength concrete, so you should expect some trouble with the struts because section is quite narrow. It is only 16 inches wide. Also concrete strength is low, so there might be some issues with the struts. Regular strength concrete exposed to weather, we are going to be designing the reinforcement for this system. So let's get into this. So the first step is the most important one because we would determine the truss model. Two important decisions that we need to do. It's going to be at the top we have compression, so there is going to be a compression strut. At the bottom there is going to be tension. This is going to be compression, this is going to be tension. So I need to determine two distances. In the previous example we choose 100, 4 inches. Again for this one I need to pick these two distances. Call this A over 2 because the strut width is going to be A and this is half of it. So make this 0.5 A. And if you, there is really no exact approach to get started. You can as well make an assumption and you can start. Right, you might assume 200, you might start. It's definitely going to be larger than 100. The forces are huge, section is pretty narrow, so it would require more thickness, more depth for the strut as well as the tie. So you can start, if you have a sectional design, if you use your software, and if you know the centroid of the reinforcement calculated by sectional method, that's a pretty good starting point. You can just give that number here, maybe pick something similar at the top, and that would be a starting point. Usually you might need a couple of iterations, it may not pass. As you can see, 900 kips applied at the top. So let me write this 900 kips. So I'm going to use some basic mechanics to make some educated guess for these two distances. I know that compression would be the same as tension, these two. And if you look at the nodal categories, the node at the top would be compression, compression, compression. The node at the bottom would be compression, compression, tension. And you know that the multiplier for this CCC would be 0.85 based on H2, and this one would be 0.70, 8570. So this distance should be larger than the other one. If everything is, calculated properly or perfectly based on the capacity, so what I can do, if this is 0.5A, this is going to be 0.5A multiplied by 0.85 divided by 0.70. Again, this is not a formal process. This is not something you have to do, but you have to do something to get started. This is one logical approach, and this is going to be 0.607. So based on this, the distance in between will come out to be 4000 millimeters minus 1.107 A. So that is distance from here to here, which is, I showed you before, that's called dV or JD. There are different notation. I can use compression blocks, so 4000 newtons times the distance, I'm just taking moments, 2125. So this is the couple, because if this is 4000, this is going to be 4000. That's the distance in between. This is the moment. That should be equal to C equal to T. So I can say this is equal to compression as well. C times 4000 minus 1.107A. You can use stress blocks. Stress blocks has nothing to do with strut and tie method, but I'm just using whatever I know to get this started. I don't want to make a random assumption. Any calculation is better than no calculation, so we'll see 0.85 times 0.70. This is just a rectangular stress block approach from reinforced concrete design. A times thickness 400, which is this thickness. So if you plug this C into this equation, you only have one unknown, which is going to be A. And from this one, A will come out to be 638 millimeters. If you picked 200, it would have been definitely fail. So I'm using 650, which may still fail. This doesn't mean that this is a good number, but it's a number to get started, which is 26 inches. This is going to be 325, half of it. And this is going to be 780 divided by 2, 390, half of it. So what I'm using is 325, 390 for these distances. I have some guidelines to make this to scale, so you can see the line, which is the top compression strut, which is this one. This is the node, right? At that point, I'm only showing half of it, so I'm not going to be solving the entire system. Distance would be 325, which is what I'm assuming, this one, 325 millimeters. At the bottom there is a tension tie, which is this line. This is the node, so this is that distance, 390. That's compression, this is tension, and strut will run in between. So it looks like angle would be pretty good, and I'm not going to be needing any stirrups. And if you look at the angle, it would come out to be, these distances important because otherwise you cannot even determine the angle, 46.4 degree, which is a very good number to begin with. And if you want to show the strut width, it would be these. And again, if you want to show strut widths, something like that. For your tie, it's going to be this width. So 390, 390, 325, 325. 390. Again, these distances you can start with anything. It's very unlikely you would have success in your first attempt. It would take a couple of attempts to pass this model. If you start with a good number, it would take less time. So you do the truss analysis. The geometry is already determined. This is the compression would be here 3840. Double check my numbers. You might find slight variations, but most of the time they would be exact. 3809. So that's what I'm seeing in my solution. Yeah, it is. Yeah, 3809. Not 40. The tension will be the same. I mean, here you are just doing a truss analysis. It's nothing other than a truss analysis. You have 4000. So, you know, this is going to be 4000. Use the angle. The distance from here to here would be 3255. Let's double check. So 4000 minus 325 minus 390, 4285. So, and you see all my trial attempts because you have to try this. This is that number. So if that's 4000, what I need to do 4000 divided by 85 multiplied by, yeah, see. So what I get now, 3805. What I have here, 3809, which is almost the same, but let's just go with the exact number. So this is going to be this way, 3805. Of course, use your software. You don't have to do hand calculations, but since this is the first example, 3805, 4000, 46.4 degree, confirmed, 5521. Let's fix this one as well. So next step would be choose tension reinforcement. I'm going to be using this number to pick that reinforcement. It's not a big task, much easier than the previous question. So again, AS would be at least tension force divided by phi S Fy. So if you do that, 3805 times 10 to the power 3, this makes this newtons, divided by 0.9 times 400 megapascal, which is 58 ksi. You would find this to be around, it may not be exact this number, but pretty close, square millimeter, which is 16.4 square inch. That's what it would require. Either number 30, number 7, or 22, number 8. So it looks like I went with 10 layers of 3 bars. This is a much critical situation because of narrow section. So we are going to be checking the centroid right at the beginning. You don't want to leave it at the end because we made some assumption for the centroid. 390, can we get it at 390? If not, we'll make the correction at this point before we proceed any further, right? So again, 1, 2, 3, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 exactly, right? So I'm not sketching it, but you got the idea. That's what I'm going with. I would calculate these distances. So what I'm doing is clear cover, which is it looks like 40 millimeter, less than 2 inches for this problem, plus straps 10 millimeter assumed, plus bar diameter divided by 2, which is 22 millimeter divided by 2. So if you do these, it's going to give you 61 millimeter. Of course, you can do this in inches. You have to be careful with fractions. So this is 61 and this is 61, right? I want to make sure that I'm not below minimum spacing. So there's a limit with bar spacing. So let's check before we start. So the spacing would be this one, S. So 61, 61, right? And we said 390 times 2, 780. So what we want for this distance is 780, because 61, 61 is perfectly balanced, and centroid would be exactly at the midpoint of 780. So this is what I want for this one. So the entire distance is 780, and I have 61 times 2 plus 9 times spacing. This is not 5, it's S, and if you calculate spacing, it's going to be 73.1 millimeter, which is definitely more than required spacing. So we are fine with spacing. So as minimum spacing would be 73.1 minus dB, which is 22 millimeter, which is going to be 55.1 millimeter, which is more than 2 inches. What we need is, based on ACI 318, we need 1 inch or larger, or we need bar diameter. So we are fine with clear spacing. Perfect. So you can do this. You can set your reinforcement at the beginning, so that would eliminate any last minute issues. If you leave it to the last step, especially for such a narrow section, you might have some surprises at the last minute. So this is the final design. We are good. If everything passes, this is going to be the final reinforcement design for this example. This is the nodal zone. Let's hatch this. Nodal zone. Give some letters. Call this node A. Call this node B. This is C. What type is this? CCC, compression, compression, compression. A multiplier is 0.85. What type is this one? CCT. Multiplier is 0.70 based on the latest H-tone. Which I also considered in my approximation here. So not a lot to check. We have a couple of checks that needs to be done, but 2 nodes, 1 strut at the top, 1 tie at the bottom. So first of all, let's check the bearing. The plate is enough. Let's start with the bearing plate. Let's start with node A. I'm just going to check bearing underneath the plate. So the plate is 400 by 800, which is 800 this dimension. First of all, I'm just specifying CCC. It is 0.85 F prime C. So that's the type of the node. I'm going to be checking BR, which is, the bearing maximum stress, which is going to be phi C 0.70 times 0.85 F prime C. F prime C is pretty low, 25 megapascal. The plate dimensions, 800 by 400. 4760 kilonewtons. Pretty close. Applied 4000, we are good. So there is no crushing under the plate. It passes. And there is other thing to check, which is this horizontal strut. Again, 0.85 multiplier. Let's calculate that PR, which is 0.70 times 0.85 times 25. Same thing. Area would be different. If you look at area 3 times 325, thickness 400. It's pretty tight, so it would pass because 3805, 3868. So we started a little bit too tight with this one. So things might fail if we move forward, but we'll see what's going to happen. So I'm done with node A. Let's check node C. I'm only checking the horizontal tie. Step 4 would be the diagonal one. So if diagonal fails, it would fail, because if horizontal comes pretty close, diagonal usually fails. We'll see. We'll come to that in a minute. Let's check node C. Node C is CCT 0.70 F prime C. That's the limit. First of all, I'm going to be checking maximum tension force, which is allowed, which is 0.70 times, again, another 0.70 times 25 megapascal times 390 times thickness 400. and hope that it should pass, because we set it up in a way that would pass. So it should pass. $38.22, which passes. And the force applied is 38.05, which is larger, which is pretty good. So that passes at node C. And then I want to check the bearing. It's a pretty large bearing plate. It should definitely pass. If the top passed with 800, bottom will pass with 1250. But let's just check that one as well. Bearing, BR. You can call this TR. That's the maximum tension, which is 0.70, 0.70, 25. Okay, perfect. 1250. That's the bearing plate size, 1250 by 400, 6125 kilonewtons. So the force we got would be 4,000 at that point. No problem. So it's done. We don't have anything else to check. So we checked this one, we checked bearing, we checked this bearing, as well as we checked this tension. So we checked all components. The final check would be diagonal strut. I'm guessing it would fail. We'll see, because we started too tight. Step 4 would be diagonal strut. Struts, but we only have one, so we are going to be checking only strut AC. That's the only check for us. So if we look at again H2 page, you can see that's this strut. So it has two ends. You can check the end at the top, you can check it at the bottom. If you want, check both, but one would be critical. Let's see which one would be critical. So it's the same strut. As you can see, there are two ends. You can check it at node A, you can check it at node C. Of course, we are going to be checking it at node A. Width is much smaller. So the width is this one at the bottom, which is much larger than the top one. So we are going to be checking at the top. If it passes, it's going to pass at the bottom as well. At node A, first of all, we need to determine the width. We need to determine that distance. Again, we need to be using the handout. It's at the top, so we are here. So we are again using LB sine theta, HS cosine theta. LB would be bearing plate length, which is 800. Let's calculate that one. So here, width would be 1250. No, not 1250, 800. Times sine 46.4 plus 650 cosine 46.4. So if you do that, 1028 millimeters. The other width would be larger, so this is going to be larger than 1028, so I'm not checking it. No need to check. That one. So and then PR 0.70 times, you need to calculate the multiplier as well, so I need that multiplier, which is 0.85 F prime C 20 KSI. So we need to calculate concrete efficiency factor, which is 0.85 minus F prime C divided by 20 KSI. So you have to input F prime C in KSI, and it has to be between 0.45 min 0.65 max. If you find anything else, just cross it out and use either the maximum or minimum. You don't want to get under or above these two numbers, right? So for this one, 3.6 KSI. Six, 7. I'm pretty good. It's oh, it's above maximum, so 6.5, which is fine. I'm going to be using 6.5. So let's fix this. I would be using this one. I cannot exceed. So PR is 6.5 times F prime C 25 megapascal times 400 thickness. I'm using the full thickness. Bearing plate also covers the full thickness. There is no need to reduce it. Times 1028. All right, so let's see. 4677. Oh, big overload. So what we got, 5521, right? So we have overload 5521, 18%, yeah. 5521 kilonewton, so which is less, not good. So this fails, which happens pretty common in certain time models. So I'm going to check the other end. Is it also going to fail? So that would dictate the solution, that would dictate the approach. Let's check the other end, see whether it would fail or not. I need to calculate, no need to check. I said no need to check, but because it is not passing, we would check to see the situation. Would be equal to 1250 times sine 46.4 plus 390 times 2, 780 times cosine this. And if you do this, I think it would be around 1443 millimeters. So again, if you want to see it, you can see it. So that is what I got. And then I would check it again, PR, same formula, 0.70. This is not going to change, it's the same, 0.65, 25 megapascal times 400, 1443. 65, 65, 66. Oh, that's very good. So it passes 5521. Good. Okay. The strut failed at node A, but it passes at node C. So it passes. This is okay. This is not good. All right, so now I'm opening up to this to debate. How would you proceed? How should I proceed in this situation? Absolutely, yeah. I think that's the easier solution, because as you can see, this larger bearing passed The issue is the bearing plate size. When you check the bearing plate, it passes. So there is no crushing under the bearing plate, but because it's really concentrating the strut at a narrow distance, by increasing the bearing plate, very easy solution. Definitely, you can do that. You can solve it by increasing the bearing plate dimension. That's my solution. That's how I did it. But any other suggestions? What else could you do? Absolutely. This 400 limits everything. So 16 inches is pretty narrow. It could be thicker. Also, F prime C is pretty low, right? So you can definitely go for 4.5 KSI, even 5 KSI. So those things definitely will improve your strut capacity. I'm glad to see my assumptions. That's also a big issue. Usually, two things fail. The assumption fails almost always because in the first solution, you never get this right. This is maybe my fourth or fifth attempt. I solved this in advance to get these distances. So these dimensions is usually a concern. We passed it. So in both cases, they passed it. So usually, if it doesn't pass, you would need to increase this. So that would change your truss geometry. So whenever you change this, it would change also diagonal compression force. So we didn't have that problem for this. It passed those two dimensions. We had a problem with the strut, and we can solve it using larger bearing plate for this problem. Okay, so these are some issues which is pretty common, which happens in every single strut and tie model. Extremely unusual. If you can pass it in the first time, ask yourself, are you making a mistake? It usually do not pass in your first solution. Bearing plate at, of course, A to maybe 1250, and it would pass, or maybe 1200, and it should pass without a problem. So I think in my solution I used, and I see 1100 by 400. I think I made this pass. So you can use that one as well. So just double check the equation. If you want to use the same bearing plate, definitely you can use same top bottom 1250, or I think you can use something smaller. And step 5, tie anchorage. I'm checking whether I need a hook or not. Sometimes the view is deceptive. Sometimes in the previous example, it looked like we have tons of space available, but it needed hook. But this time, it looks like we have very short distance. It may not need a hook. So I'm going to be checking it at this point. This is my available distance, so I'm going to be checking it with regards to the required length. Let's just do a little sketch. Something like that. There is a force. Centroid is here. This is 3805 kilonewton from this point. Angle 46.4 degree. So I'm going to be checking development starting from this edge. Reinforcement can be extended to the edge straight minus side cover. Again, side cover assume 40 millimeters, slightly less than 2 inches. So the full distance was 1250, so this is 40 millimeters. Bearing plate was 1250 divided by 2 minus 40, that is going to be 585. 585. And then this one is going to be 625. And this little distance would be 390 times cotangent 46.4 degree. $371. So I'm going to say length available for development, LD available, would be 585 plus 625 plus 371. 1581. What's required? Straight bar development length. So if you calculate this, which is Fy, we are at the bottom, so there is no 1.3 multiplier, it's just one multiplier. 1.7, 1.0, so just use your equations, this is nothing new. 1045. See, it's not going to require. It looks super tight. If you look at the figure, it looks like it's going to need it, but no. Straight bars would be fine. No hook needed. Just cut it straight. It's going to work because the strut is such wide strut. You are checking it at this point, which is pretty good. No problem. No hook needed. Some routine step. This is 400 thick. It's a thin member, so I'm not going to put anything inside. The previous one was a thick member. I will just go with 2 layers. 2 layers of number 4 for this system. Vertical will be the same as horizontal, so vertical horizontal is the same. 2 times bar area 125 square millimeter. 2 legs divided by member thickness 400 millimeters and spacing is this, and make it 0.3%. So if you calculate spacing, 215. Yeah. Use number 4 at 215, which is 8 inches. I mean, if you are finding this to be too frequent, you can go with number 5333. It's not permitted. You cannot exceed 300, but you can always use 300. So pick your numbers. Both should work. Yeah, 12 inches. Of course, it's always, a better approach to use smaller bars. So this would be a little bit better in terms of service performance. Better for serviceability. The final step, additional checks. We don't have anything. So as needed, if you have any additional code checks, if any, sometimes there are certain requirements for certain members. Not strut and tie, but general requirements do here. That's step number 8. So it's already sketched. Main reinforcement, which is at the bottom, we are putting 30 number 7. As you can see, you can design a bridge element by hand calculation fully without using computers, and your design would most likely be better than your computer sectional design, because there are so many details you are considering which computer or sectional design wouldn't even consider at all. The minimum the amount of hooks, the happier contractors are. So this is the main reinforcement. That's pretty much it. That's the full design. I'm just going to be putting crack control reinforcement. Of course, you want to put one at the clear cover location. I mean, as if you are putting a main reinforcement. So it is here. The second one, you can see all these lines. They correspond to crack control. I mean, it's pretty significant crack control reinforcement. For older systems, we don't see it. We don't have crack control reinforcement, so penalties would apply. You would go with 0.45 multiplier. We use 0.65 for this. If you didn't have crack control reinforcement, many things would have failed for this model. Something like that. And of course, I'm not going to go super detailed with the vertical one, so I'm just going to show a couple of vertical crack control reinforcement. But the spacing is the same, vertical and horizontal, right? To number 4 at 8 inches, both vertical as well as horizontal. You can always put additional reinforcement, and for such narrow members we really like to put U-bars at the edges to prevent any splitting. Same spacing, but some U-bars at the edges to confine. This would be good for both serviceability as well as ultimate limit state. So what I'm putting is number 4 U-bars. Again, you can use the same spacing, 8 inches, if you want to prevent edge splitting. It has nothing to do with strut and tie model, but this is just a good design practice. So again, you can put it, you should put it on this edge as well. As you can see, crack control reinforcement is such a narrow section, so it looks like I used 2 U-bars. So this is the crack control reinforcement, number 4 at 8 inches. Some overlap to provide continuity, but I mean, if you want to hook it, it's fine. The code allows you to hook it, so you can use straight bars. You can hook it this side, but then your member would not be confined, so you are applying significant compression. So again, the U-bar would be perfect. So this closed stirrup pretty much serving as the same purpose. You have a U-bar which confines the section. So I would much prefer not going with a hook, but a solid U-bar for crack control. All right, that's pretty much it. Thank you very much for your attention.